All right, hello, Calc BC. Welcome to lesson 3.4 titled The Average Value of a Continuous Function or Average Value of a Function. This comes from Unit 8 of the College Board's course and exam description. Now remember, our Unit 3 covers the entirety of integration from A-B content, but you did not cover Unit 8 due to the shortened school year last year. So this is our first brand new lesson. We're going to little by little go through all of these topics in Unit 8, which is all about applications of integration. So we're going to start out with 8.1, finding the average value of a function. Again, this is our lesson 3.4. And down here, this is the College Board's kind of overview of this lesson. And I want to specifically talk about the essential knowledge here. It says the average value of a continuous function, f, over an interval from closed a to b is 1 over b minus a times the integral from a to b of f of x dx. And this lesson is going to be all about interpreting that, figuring out exactly what that means. So I'm going to pause right here and we'll head over to the notes. All right, so here are our notes, 3.4, average value of a continuous function. First off, we have the mean value theorem for integrals, and it says that if f is continuous from a to b, then there exists some number c, an x value, between a and b, such that the integral from a to b of f of x dx equals f of c times b minus a. Now, I know that's a little bit complicated language there, but this next section I think really kind of breaks down exactly what this is saying. And I really like this, so let's take a look at this. The geometric interpretation of the mean value theorem for integrals is that for a positive function f, there is a number c, remember that's an x value, between a and b, such that the rectangle with base from a to b and height f of c has the same area as the region under the graph of f from a to b. In other words, c is the value of x on a to b where you can build the perfect rectangle, a rectangle whose area is exactly equal to the area of the region under the graph of f from a to b. Okay, again, that was a little bit of a wordy paragraph, so I'm going to give you this visual to hopefully make this clearer. So what I've drawn here is two straight lines that are the same line on coordinate planes. And I'm just randomly marked an A and a B, all right? So in this first graph, doesn't matter what this line is, what the equation is, but we know that if we were gonna find the integral from A to B, it would be the area under the curve, right? So I'm going to just kind of shade that in for us. And there's some area there that is the area under the curve, and that's our integral, right? So the idea here is that what if we just took that area and instead of making the shape that kind of fit under this curve, what if we made it into or forced it to fit into a rectangle? And our rectangle is still going to have a width from A to B, but the height is going to be whatever the height needs to be so that this whole area fits. And so in this case, since it's a straight line, it's going to be kind of clear, hopefully, that if we forced it to be a rectangle, it's going to look something like this, where we kind of have this triangle down here and this triangle up here that replaced each other from the original. So you can see that the two orange regions have the same area, but the second region is a perfect rectangle, we could say, with the width from A to B, and the height here is kind of magical because it's telling us on the y-axis what we are calling f of c, which is the average value of the function. It is the average y value from an x value of a to an x value of b. So if we kind of think about this whole purple line from a to b, the average of the y values is this f of c, which in this case, since it's a straight line, should be halfway between down here and up here, which makes a lot of sense, right? So if we wanted to kind of write out what the area of this perfect rectangle would be, it would be b minus a, which is that base, times the height of the rectangle, which we're calling f of c. And that's kind of where this mean value theorem for integrals comes from. So think about it. Over here, we have that magic rectangle with f of c and b minus a. And that's going to equal the integral from a to b of f of x dx. So this is just saying, this mean value theorem for integrals is just saying that these two orange areas are the same, okay? So what we're going to be able to do after this is figure out, just based off of a given function and two endpoints of an interval, we'll be able to figure out what the average value of the function is, the average y value, or this f of c. Even if it's not a straight line, we'll be able to find the average value from a to b. And this is the formula, because think about, if we had our area was b minus a times f of c. If we wanted to find that f of c, we could divide the b minus a to the other side. So we have 1 over b minus a times the integral, right? That integral is what was equal to f of c times b minus a. So all this average value formula is coming from is this dividing the b minus a to the other side. Okay, so let's try to apply that formula in this first question here. We were given f of x equals 1 plus x squared and the interval -1 to 2. We wanted to find the average value. Just think that a is -1 and b is 2. And we're going to use this formula. So we have f sub AVE. So AVE is just standing for average. This is just common notation to mean the average y value. We're not ever plugging in for A or for V or for E or anything like that. It just means the average value. Equals, so 1 over b minus a, so it's going to be 1 over 2 minus -1. And then the integral from -1 to 2. And then we can plug in the function 1 plus x squared dx. And if we solve this, we should get the average value of f on the given interval. So let's try it. So 1 over 2 minus -1 is 1/3. This suspiciously also kind of looks like the formula to find the average of something, right? Because think about, like, we're dividing by 3, and 3 is kind of like our width, which is kind of like the number of numbers if you use the formula for an average, but we don't really need to do it that way. But let's keep going. So we have then the integral of 1 plus x squared, which is going to be x plus x cubed over 3 from -1 to 2. Okay. So then we can plug in the 2 and plug in the -1. It's going to be 2 plus 2 cubed over 3 minus -1 plus -1 cubed over 3. And that's going to equal 1/3 times, and if I kind of add and multiply here, we get 14/3 minus, and then this one becomes -4/3. So it becomes 14/3 plus 4/3. So we get 1/3 times 18/3, which is 18 over 9. If we multiply across, 1 times 18, 3 times 3, and that's 2. So we found the average value of f, and it is 2. So that's the average y value. Letter B says to find c. So remember, c is an x value. So now we're finding the x value that gives us that average y value. So if we think back to our original function, we now know that there's some f of c that's 2. So what we can do is set the function equal to 2 to find the x value. And then we can subtract 1 to the other side, and we get 1 equals x squared. Square root both sides, you're going to get x equals plus or minus 1. We need to make sure that that's in our interval from -1 to 2. Remember, up at the top, c is a value from a to b inclusive of the a and the b. So since one of our endpoints is -1, we can still have -1 as our c. So we're going to have a c of plus or minus 1. Both of those values work. They're both in our interval from -1 to 2. And this is the part I really like, looking at this on the graph. So on the graph, I sketched this function already. So 1 plus x squared, and the endpoints were -1 and 2. So I drew vertical dotted lines there to show you that that's the endpoints of our interval. And we found that the average value, the average y value in this interval was 2. So what we should be able to do is draw a horizontal line with a y value of 2. And we're sketching the rectangle whose area is the same as the area under the graph. So if I kind of connect this to the base here and make a rectangle, the area of this rectangle is the same as the area under the curve. So if I also shaded in the area under this curve from -1 to 2, it would be the same as the area of this rectangle. What that means geometrically at this point is that the area in here, in this kind of U shape up here, is going to have to be exactly the same as this area of this almost triangle up here that's cut out of the rectangle. That looks like it could be true, and it is. What we can also see here is that we found these C values that have their x values that have a y value that is supposed to be the same as the average value. And you can see at -1 and at +1, we have y values of 2, which was our average value, right? One more practical thing that this shows us is that for the curve from -1 to 2, the average y value of all these y values, if we could somehow add up every point along this curve and find the average of the y values, the average would be 2, right? So that's what we're figuring out there, okay? Very cool. Let's take a look at the next example. The table below gives values of a continuous function f. Use a left Riemann sum with 3 sub-intervals and values from the table to estimate the average value of f from 5 to 17. All right, so let's first just write this out using the formula. So we have f average equals, and it's going to be 1 over, the interval is from 5 to 17. So it's going to be 17 minus 5. The integral from 5 to 17 of f of x dx. And we are supposed to use a left Riemann sum with 3 sub-intervals. So let's write that out. We have 1 over 12, and here comes our integral. We don't know the equation of f of x. We're going to have to just rely on the table and hope for the best. We know that it's continuous. That's a good sign. That means we're allowed to use this formula. And that means hopefully our Riemann sum is going to be fairly accurate. So for the first part of the Riemann sum, the first bar, the width is going to be from 5 to 9, which is a width of 4. And the height, it's going to be a left Riemann sum. So the height's going to be this 23 right here. The second bar is from 9 to 12, which is a width of 3. And the height is the left endpoint, which has a y value of 29. And the third bar is going to be from 12 to 17, which is a width of 5. And the height is going to be the left endpoint, which is 36. So that is an approximation of our integral. So that's going to have to do. So we're going to end up with 1 over 12 times, and if you kind of multiply these out, you get 92 plus 87 plus 180, which is 359. And that's going to just be 359 over 12. That's the reduced form of that exact answer. If we approximated this and wrote it as a decimal, we get 29.917. And I write that out because that's a good way to kind of sort of check ourselves. And we can look at these y values that were given and think about, okay, does it make sense that 29.917 could be the average of these y values? And it's in the right range, so I would say yes. Looks like it could be about right, okay? So that is the answer to that example. And let's move on to the next page. We have 3 more examples to go. All right, this one says, a study suggests that between the hours of 1 p.m. and 4 p.m. on a normal weekday, the speed of the traffic on a certain freeway exit is modeled by the formula S of t, where the speed is measured in kilometers per hour and t is the number of hours past noon. So 1 p.m. would be t equals 1, 2 p.m. would be t equals 2, etc. Compute the average speed of the traffic between the hours of 1 p.m. and 4 p.m. Okay, so the speed of the traffic is S of t. So if we're finding average speed, we're just finding the average of this function. So this doesn't require us to take the derivative. You know, sometimes when we think about speed, we would think about velocity, which would be the first derivative. But in this case, the speed is S of t. That's what's given to us. So this isn't like a position function that we would have to take the derivative of. We already have the speed function. But to find the average speed, we're going to use our average value of a function formula. So we have f average equals 1 over, we're going from 1 p.m. to 4 p.m., which is going to be from t equals 1 to t equals 4. So I'm going to go 1 over 4 minus 1 times the integral from 1 to 4 of S of t, which is 2t cubed minus 21t squared plus 60t plus 20 dt. And the question says to use a calculator and give our answer correct to 3 decimal places. So here is my calculator screen. And let's type this in. So I'm going to first grab a fraction and do 1 over 4 minus 1. And then I'm going to go into math 9, which is a specific definite integral. And I can put my bounds in. And then I put in the function. I'm just going to use x to represent the t. And then because I'm using x's, I'm going to write dx. That looks perfect. So I'm going to press enter. And we get 65.5. So we were told to round to 3 decimal places. Lucky for us, we're going to be able to do an exact value here because it's only 1 decimal. So we can just put 65.5 kilometers per hour because that is the average speed. And we were told that speed is kilometers per hour. And there we go. We figured it out. Nothing more to do than that. Great, let's keep going. Next example. Suppose that during a typical winter day in Minneapolis, the temperature in degrees Celsius X hours after midnight is shown in the figure below. We are not given an equation this time, so we have to rely fully on the graph. Use a midpoint Riemann sum with 4 equal subintervals to approximate the average temperature over the time period from 4 a.m. to 8 p.m. Now, first of all, 4 a.m. to 8 p.m. Is going to be what? So it's X hours after midnight. So it's going to be from X equals 4 to X equals what? 8 p.m. is going to be 12 plus 8. So it's going to be 20. All you 24-hour time people most likely already knew that. 9, 10, 11, 12, yeah. So we're going from 4 to 20. And we are going to be finding, first of all, the average temperature. So let's write that out, first of all, using our formula. So A is going to be F average, which is going to be 1 over 20 minus 4, integral from 4 to 20 of f of x dx. We don't know f of x, so I'm just writing it as f of x as a placeholder. And we're just supposed to be doing midpoint Riemann sums with 4 equal subintervals to figure this out. So we know it's 1/16, but I don't know what is going on in between. We know that there's going to be 4 subintervals, and I'm going from 4 to 20. So let's think. We need to split that into fourths. So I'm going to go from 4 to 8, from 8 to 12, 12 to 16, and 16 to 20. So I'm going to have intervals with width of 4, and they're midpoint sums. So let's think. From 4 to 8, I'm going to be using the y value at 6 to make a bar. From 8 to 12, I'm going to be putting a y value at an x of 10 for the bar, something like that. Let me just kind of shade these in so you can see them. From 12 to 16 will be wherever the 14 is, so right about up here. And then from 16 to 20 will be wherever the 18 is, so somewhere right around here. All right. So this is going to be a little bit of guesswork because we don't know exactly what the y values are, so our answer is definitely not going to be perfect. We're just estimating here. And I'm going to kind of pick what I think the y values might be. Maybe you think it's something else. But I think so that we can all kind of make sure we're checking our work accurately, let's just kind of go with what I write here since we're doing this over video. So let's see. For the first bar, we are always going to have a width of 4. And this y value right here, I think, is right around -5. Because it goes 4, 5, 6, 7, 8. So it's right around halfway between 4 and 6, -4 and -6. The next bar has a width of 4 and a height of about 1. The next one has a height of approximately 2. And the last one, maybe that is close to, I don't know, -1.5. Yeah. Okay. So then let's see what happens. So we got -20 plus 4 plus 8 minus, hold on, 36, yeah, -6. -20 plus 4 plus 8 minus 6. So we add those together. We get 1/16 times -14, which is going to be -7/8, or -0.875 degrees Celsius. So that's an approximation of our average temperature from 4 a.m. to 8 p.m. Letter B. Use your answer from A to estimate the time when the average temperature occurred. So now we have to think about that. This -7/8, -0.875, is a y value. So on our y-axis, we're talking about something that's a little bit less than -1, or a little bit more than -1, I guess you could say. So it's right around here, right? And so we're looking on our curve for when did we cross that y value. And it happens twice, once right here and once right here. So if we first of all just think about from 4 to 20, does it make sense that that line right there would indicate the average y value from here to here? And I'd say, yeah, that's probably pretty close. It's about halfway between, a little bit more, but the curve also isn't exactly perfect, so that makes sense. It could be about there. That's a good approximation. It's at least in between the highest value and the lowest value, so that's good. So let's just kind of guess what these x values might be. So let's see. It's 8, 9, 10. It looks like it's halfway between 8 and 9. So maybe it's like 8.5. And then over here, it looks like maybe it is, I don't know, halfway between 17 and 18. So 17.5. These are complete guesses, so it's very possible that you might think it's something different, but kind of close, and that's fine. You can write it a little bit different if you want for this part. But then, okay, so we got 8.5 and 17.5, but the question said estimate the time. So let's change this into times. So 8.5 hours after midnight would be 8:30 a.m. And 17.5 hours after midnight, so think about 12 would be noon, and so that's 5.5 more, so that'd be 5:30 p.m. Okay, there we go. There's our times when the average temperature happened. All right, let's keep going. One more question. Find the average value of the function on the given interval without integrating. Graph and use geometry. So first of all, we're going from -1 to 6. So if we just wanted to write out the formula, it would be 1 over 6 minus -1 times the integral from -1 to 6 of f of x dx. So we know we start with 1/7 times something. But what does it times? And the question says, don't try to integrate. Let's graph and use geometry. So let's try to graph these. So I'm going to assume that each of these kind of tick marks goes up by 1, because that'll work for this. And so we're going to graph from -1 to 3. On the x-axis, we're going to graph the function 3 minus x. So if I plug in -1, I get 4. If I plug in 0, I get 3. If I plug in 1, I get 2. If I plug in 2, I get 1. And if I plug in 3, I get 0. So it's a straight line with a y-intercept of 3 and a slope of -1. And then from 3 to 6, we're going to graph 2x minus 6. So 3 is 6 minus 6 is 0. At 4, we have 8 minus 6 is 2. 5, 10 minus 6 is 4. And 6, 12 minus 6 is 6. There we go. So we have two kind of line segments that make up this function. And we have to integrate from -1 to 6 this function. So we know what to do, right? Integration means the area under the curve. So let's see if we can figure out the area of these two regions. And hopefully it's pretty clear that those are two triangles, right? So we're going to do 1/2 base times height. So the first one over here has a 1, 2, 3, 4. 1, 2, 3, 4. Has a base of 4 and a height of 4. So it's going to be 1/2 times 4 times 4 plus 1/2 times 1, 2, 3 times 1, 2, 3, 4, 5, 6 for the height. Okay, so we have 1/7 times 4 times 4 is 16, divided by 2 is 8, plus 6 times 3 is 18, divided by 2 is 9. And so now we have 1/7 times 9 plus 8 is 17. So we have 17 over 7. That's our average value of the function. Now, if we wanted to kind of check the realisticness of this, we could divide and we get a decimal of 2.429-ish. And if we take a look at the graph over here, that would be 2.4 right about here. And if you think about this line and this line segment, it kind of makes sense. That is pretty good, seems like a pretty good estimate of the average y value that would exist for that whole interval. And it's true. It is the average y value because we just figured it out geometrically and algebraically using the formula, right? So there we go. That's how you find the average value of a function. So you have some practice problems to try. Thank you so much for watching, and let me know if you have any questions. Thank you very much.